I'll begin by interpreting the problem statement. We have kerosene at 20 degrees C flowing through a Venturi nozzle. This pressure gauge measures a differential pressure of 20 kPa. The kerosene velocity at this point is 10 meters per second, and the goal is the velocity at this point. Next, I'll connect the problem to what I already know. This is an open tube. This hole in the wall is called a pressure tap, and this arrangement allows the pressure gauge to sense the pressure at this point and to sense the pressure at this point. Converging streamlines in this region of the nozzle provide a tip-off that I can apply the Bernoulli equation to the flow in the nozzle. Also, I recall that I can apply the hydrostatic equation across here because the streamlines are straight and parallel. Similarly, I can apply the hydrostatic equation across here. This is how I document my situation. Notice that I label point 1 and point 2 on the center streamline, which is here. Notice my fluid property here. I actually wrote this down later in my process when I recognized what property I would need. The goal is the speed at point 1. This is right here. To find an idea, to reach my goal, I recognize that the Bernoulli equation applies. I sketch the streamline. I label points 1 and point 2. I select the head form of the Bernoulli equation and I write down the general equation. That's right here. Next, I'll do term-by-term analysis. My goal is right here. The velocity at point 1. The velocity at point 2 is known. The differential pressure is unknown. And the elevation terms there and there go to 0, and I should go ahead and label my datum like this. I write down my reduced equation. My new goal is the differential pressure between points 1 and 2 on this streamline. To find the differential pressure, I'll apply the hydrostatic equation. I sketch the points of interest, then I apply the hydrostatic equation from point A to point 2. Next, I apply the hydrostatic equation from point B to point 1. I notice that gamma delta Z will appear in both equations, thus I write, now the pressure at B minus the pressure at A is specified. Therefore, I can easily find my goal. Notice that I justify my conclusion. Explaining why is good engineering practice. Now I have two equations and two unknowns, so my plan is simple. I'm simply going to stuff numbers into the Bernoulli equation. I rewrite the Bernoulli equation. I insert numbers, carry and cancel units, and the answer is 7.13 meters per second. I believe that sketching is essential for engineering analysis. For example, this sketch shows how I'm going to apply the Bernoulli equation, and this sketch shows how I'm going to apply the hydrostatic equation. When I see a pressure gauge or a manometer, I nearly always do an analysis. For example, here's the analysis I did for this problem. Review comment number 3. When I see flow in a pipe and I see straight and parallel streamlines, for example, straight and parallel streamlines across here, straight and parallel streamlines in this region, and straight and parallel streamlines here, I recognize that the pressure variation will be hydrostatic. This concludes the example. I hope you have found this useful. We'll see you next time.